Okay, so what we're going to go over today is simple harmonic motion. Right? What simple harmonic motion is any motion that essentially repeats itself over and over. Right? So my multi-purpose ghetto physics demo here is now going to go from being a circular motion demonstration to a simple harmonic motion demonstration. Saving taxpayer money all over the place right now. Okay, so this is a pendulum. Okay, it's moving with simple harmonic motion. It's following the same path over and over and over again because there is a force that wants to pull it back to a position of equilibrium. Where would the position of equilibrium be for a pendulum? Yeah, right in the center, because that's where it would rest if not disturbed. Okay, so this is an undisturbed or equilibrium position. Okay, the only reason it undergoes simple harmonic motion is because somebody disturbs it. Okay, by moving it away from equilibrium. Does that require work? Yeah, I have to exert a force or a distance. Okay, what tries to bring it back? Yeah, well, yes and no. Gravity, yes, but a component of gravity that acts back towards equilibrium, because gravity wants to pull it which way? Down, but the string prevents that, right? So there's this like kind of net force component that is acting back towards equilibrium that is in fact always changing. Okay, what's happening to that component of gravity the further from equilibrium I get? It gets bigger, right? Because if I get out to here, it's equal to gravity, because now gravity is acting straight down, and that's the way this thing would want to move. Okay, no pendulum swings this far out. Okay, like if I let go of this, it's not going to swing along the arc. It's going to what? Now it's going to drop until the tension in the string takes up. Okay, simple harmonic motion actually for a pendulum only occurs through a narrow arc. Okay, after that you get too many floppy kind of gravity-induced motions. Okay, so a true pendulum really only swings through about like 10 degrees, maybe 15. Okay, you get outside of that and it starts to get a little bit off. Okay, does that make sense? All right, so simple harmonic motion happens because there's a restoring force that's trying to restore equilibrium. That is, it's trying to bring the pendulum, or whatever else is moving with simple harmonic motion, back to equilibrium. The problem for a restoring force is it will always fail. Well, sort of. It succeeds in that it gets the object back to equilibrium, but then what happens? So I disturb the pendulum out to here and I let it go. It goes back to equilibrium, and then what? It just keeps right on going, okay? Because it builds up energy, right? I've got potential energy here. I let it go, that potential energy turns into kinetic, and it goes right on through equilibrium, turning that kinetic energy back into potential. And that force, that restoring force, increases, stops it, and then pulls it back to equilibrium, and then builds up that kinetic energy again. Okay, so simple harmonic motion, in the absence of any non-conserved forces, should continue forever. Okay, because you're really just converting one form of mechanical energy into another. Okay, everybody all right with that? But obviously all pendulums eventually stop swinging. Like I'm actually making this thing go by giving it a little push each time it goes through equilibrium. Okay, if I didn't do that, it stops quite a bit quicker once I stop helping it. Okay, is that making sense? All right, so the two examples of simple harmonic motion that we're going to look at are the pendulum and a mass on a spring. So if I had like an air table, okay, a frictionless surface, and I had like a bowling ball and a big spring, and I pushed the bowling ball on the spring so that I compressed the spring, and then I let it go, that whole system is just going to go back and forth, right? Okay, because when I compress the spring, am I doing work? Okay, so that's putting elastic potential energy into the spring, and then when I let it go, the spring does work and pushes the ball, sends it right past equilibrium, which would be the unstrained length of the spring, and it'll just go right on out until it stretches the spring, and the spring pulls the ball back, pulls it back to equilibrium, shoots right through, compresses the spring pushes really hard, stops it, and then it just keeps going. Okay, so it all involves energy. So this whole idea of mechanical energy and work energy theorem, that's going to come back, but in a kind of a different form. Okay, we're going to be looking at elastic potential energy, and then kinetic energy, same as before. Okay, a little bit of work energy theorem, force and distance, all that stuff still comes into play. We're not going to cover any of that today. We're just going to look at the basic principles of these two examples of simple harmonic motion. All right, what would I call the amount of time it takes the pendulum to make one complete oscillation? Exactly. So that term is going to get used again in this unit. And what do I call the number of oscillations per second? Frequency. Cycles per second. Okay, so I'm going to be using both of those. Frequency quite a bit more in this unit than we used it in the last unit. We like named it in unit 3 and then never used it. Okay, well it comes up a lot when we're talking about waves and simple harmonic motion. Frequency is a very important property of both of those. Okay, so a playground swing moves back and forth over the same pass. Okay, a guitar string, another example of simple harmonic motion. If you pluck the guitar string, the tension in the string acts as a restoring force, and the string wants to go back to its equilibrium position, but it'll go right past it, and it'll oscillate back and forth, making pretty sound waves, okay, that everyone can hear, and that go into the resonance cavity of the string instrument, so whether it's a guitar or a violin or bass or whatever, okay, that whole wooden hourglass-shaped part is the resonance cavity. Okay, the waves from the string travel into there, and they are reflected around and amplified through interference, and then the whole body resonates, and you get a greater sound, okay, than you would if you covered the hole and just plucked the string. Okay, it's kind of the difference between plucking the string on an acoustic guitar and plucking the same string on an electric guitar that's not plugged in. Okay, you get almost no sound at all from an electric guitar if it's not plugged in, because there's nothing to amplify the very tiny little waves that the string actually makes on its own. Okay, so you either have an electric guitar with a microphone or a pickup that takes that and then electrically amplifies it, or you have an acoustic guitar that uses the waves, channels them into the resonance cavity and amplifies them that way. Okay, all right. So if I'm looking at a mass on a spring, okay, this dotted line here would be my equilibrium position. Okay, and so the mass, if I pull it out past equilibrium, okay, that will involve doing work, and the spring will want to pull it back. So when I let it go, it'll travel back to equilibrium, through equilibrium, to this position here. Okay, and it'll stop, and then it'll go back to equilibrium again. This distance and this distance are equal. Okay. The object, in a horizontal example, will travel the same distance past equilibrium in both directions. Okay. The maximum distance from equilibrium is called the amplitude. Okay. It's the maximum excursion from equilibrium that the object or particle makes while oscillating. Okay. The greater the amplitude, the greater the energy involved, because the more you'll have to compress the spring. Okay. All right. So if I start out here, when am I done a full oscillation?
After someone goes forward, comes back, and then once it goes back to the equilibrium, you go back as a backflow.
Nope, that would be 1 1/4. Okay, so if I start here, I've got to go out to here and back. That's one full cycle, because I've gone from my starting point back to my starting point again. So that's one full cycle. If I went back to equilibrium, Tegan, as you suggested, that would be another 1/4 of a cycle. Does that make sense?
Yeah.
Okay, so this is if I get out to here, to the other side, to the opposite side, that's half a cycle. Okay, and then back again is a full cycle. So the amount of time that would take would be the period. The number of times it does that in a second would be the frequency. All right, everybody okay with those ideas? All right. Right. That's all I need to mess up. Yeah. Uh-oh. Don't quit. discombobulated. Okay, so in each case, the pendulum and the mass on the spring, there's an equilibrium position. That would be the at-rest position, okay, of the object. It's where it would sit if it wasn't disturbed. It's the undisturbed position. Okay, if you pull it away from there, a force in the system pulls it back. We call that force the restoring force. Okay, without a restoring force, simple harmonic motion does not occur. And that restoring force has to vary linearly with displacement. That means if I am at equilibrium and I move to 1 meter from equilibrium, okay, I'm going to require X amount of force. If I move 2 meters from equilibrium, I require 2x that force. Okay, so it varies linearly with displacement. Right? So as I increase my displacement, I will get a linear increase in the amount of force that is required to move it. Okay, and that is because of something called Hooke's law, which we'll talk about another day. Okay, but it's related to this idea that a force is required. Okay, so if it's a pendulum, that force might be the component of gravity acting along the arc. If it's a mass on a spring, it's the force in the spring, the tension in the spring. Okay, are all springs the same? No, all springs are different. Okay, all springs have a different spring constant or stiffness. Okay, for example, the spring in a ballpoint pen, okay, cannot do the same job as the springs in your car. They're both springs, but one is considerably stiffer than the other. Okay, were I to interchange them, your car would destroy itself, and your clicker pen would be impossible to actuate, okay, because you would not be strong enough to move the spring. Okay, so every spring has a different spring constant, okay, or K is what we use to represent that. So if I'm looking at a mass on a spring, what do you suppose are the things that could affect how long it takes that spring to make one full oscillation?
Here's the mass.
The mass, and let's say it's frictionless. You're right, if I had friction, but it would work equally on both sides. So totally frictionless system, mass and the thickness of the spring. Yeah, okay. The spring constant. Imagine spring on your car, spring from your pen. Okay. If I put a mass on both of those springs and set it oscillating, okay, the spring from your car is going to do this, and it's going to be done. It's hardly an oscillate at all. Okay. That same mass on the spring from your pen is going to go, and it's going to way out there, and it's going to come way back again, probably destroy the spring because it's very light. Okay. All right, so those would be the two things that would affect the period of the spring. Now, I had mentioned this before. In order for simple harmonic motion to occur, the restoring force has to vary linearly with displacement. Okay? That is, it has to increase the further from equilibrium we get. Displacement is measured from equilibrium. Right? So it can be on either side. Okay, so this is something we've already talked about, but the period is the time needed to complete one cycle, okay, and the maximum distance from equilibrium is the maximum amplitude.
Why is water so heavy? Is it because it's like condensed?
No, you can't, liquid water you can't pressurize. You can't compress a liquid.
No, but like, why is it that when you have more of it, it like gets heavier?
Well, it's same with
Its
anything.
apparent weight is like exponentially, almost like sand or anything like else.
It's not exponential. If I have more, I just have more of it. Water just has a certain density.
So it's just like more of its apparent weight. Because like apparently,
No. Water just has a certain density. More of it just means there's more of it. It's linear.
But like milk doesn't make sense.
But milk has other things in it. It's not all water. If you had an equal volume of water and milk, the water would be heavier than the milk because the fats would be lighter, right? So if I had an equal volume of milk, only part of that milk is water. The rest of it is the fat. So it might not weigh as much, even though it's the same volume, because it's not all water. Yeah? Does that make sense? All right, so if I'm looking at this here, okay, remember that this is our equilibrium position, okay, you're across the middle, right? If I get away from that equilibrium position, the spring will push harder or pull harder, okay? So in this situation, the spring will be pulling harder. In this situation, the spring will be pushing harder, but the force would be equal. Doesn't matter whether it's pushing or pulling, the force would be equal at those two positions, and the acceleration and force would be at their maximums, at the maximum amplitude, because that is where the spring is stretched or compressed the most. How fast is it moving at those two positions? Right, because that's where it stops and changes direction and starts coming back. Where does it move the fastest? At equilibrium. Okay, how much force is there at equilibrium? Right, because the spring is neither stretched nor compressed at equilibrium, so it doesn't exert a force at equilibrium. Okay, what kind of energy would you have here? Potential. What kind of energy would you have here? Kinetic. What if you were partway in between? Then you have both. Right. Okay. It actually ends up being like a roller coaster. Right? You'd have your potential energy, your kinetic energy, okay, at the different places along the way. All right, so if we are talking about a mass on a spring, we can calculate the period of a mass on a spring with this formula. 2 pi times the square root of m over k. So the two things that can affect the period of a mass on a spring are the mass and the spring, oddly enough. Okay? So the period of a mass on a spring is affected by the mass and the spring. If I put a greater mass on the same spring, it would make it go further, and as a result, take longer to do one full oscillation. Okay? All right, so that formula looks like this. T equals 2 pi times the square root of m over k. All right, so if I want to manipulate that equation for anything that's under the root, what do I have to do to everything first? Square it. Okay, so if I'm trying to solve for m, I have to square everything in that equation before I do anything. That'll get rid of the root, but it will square everything else. So period will be squared, 2 will be squared, pi will be squared. Okay? Everyone all right with that idea? Okay. So is that going to be a terribly hard formula to manipulate? Okay. So once I square everything, I would just have t squared equals 4 pi squared times m over k. And I just do algebra. Okay. Once you get the squaring part out of the way, it's pretty easy from there. Okay. Now, units. Mass is in kilograms. Okay, so it's still in kilograms. And the spring constant is in newtons per meter. Okay, the number of newtons required to extend or compress the spring by 1 meter. Okay, everyone all right with that idea? All right, so if we're looking at a simple example here, we have a ball that is a mass of 0.2 kilograms attached to a spring that has a tension of 28 newtons per meter. Ball is released from its equilibrium position, so it will fall and then bounce back up and return to equilibrium. That'll be one full cycle. Okay, we can calculate that period by simply plugging in the numbers into that formula. So T would equal 2 pi times the square root of 0.2 over k, which was 28. Okay, so that would give us the period of that oscillation, which would be 0.53 seconds. So it would take just over half a second for it to go down, up, and back to equilibrium. Okay. Making sense? Okay, let's give you a 4-minute break here, and then we'll get back to this in a second. Okay, so what things would affect the period of a pendulum? Length of it, for sure. Gravity. Anything else? Usually people will say the mass of the object, because that's our gut reaction. It affected the other one. Why wouldn't it affect the period of a pendulum? So my question to you is, why wouldn't it affect the period of a pendulum? Because it doesn't. Do all things fall at the same rate regardless of their mass? That's exactly why the weight of a pendulum doesn't make any difference, or the mass, sorry, of a pendulum doesn't make any difference, because all things are affected by gravity equally. Okay? So the two things that affect the period of a pendulum are its length and the acceleration due to gravity. Okay? Which can be like pretty obvious. If I use the full length of this pendulum, okay, and set it in motion, it's got a fairly long period. Okay? But if I suddenly do this, did that period just get a lot shorter? Yeah. Well, I'm still on Earth, so that didn't change. All that changed was the length, okay? And the length really affects the period of the pendulum. The longer the length, the longer the period. What about with G? If I increase G, what happens to the period of the pendulum? It'll get quicker. Yeah. The period of the pendulum will get smaller. Okay? That's what I mean by quicker. The amount of time it takes to oscillate will be less, because it won't oscillate as far. Okay? So if I have this pendulum on Earth and it does this, okay, that's what it looks like on Earth. If I do that on the moon, it'll be like this. You get the idea, I don't have to go through this thing. Okay. It'll be really, really slow, because gravity on the moon is 1/6 of what it is here. Okay, so it'll take way longer in low gravity for that pendulum to complete an oscillation. If I was to do that on Jupiter, it'd be like, okay, super quick, because Jupiter has way more gravity, and so it wouldn't get out as far before coming back, and the pendulum would be, the period would be really, really small. Okay, so very similar formula in terms of its structure. It's just what's in it is different. Okay, period on this one equals 2 pi times the square root of now length over gravity. Okay, we manipulate it in the same way. Okay, so that's the good thing, is the period of both of these oscillators is essentially affected in a similar way. The formula is very similar. All right. Okay, so we'll just go along like that. Now, some terminology here. Okay, terminology for a pendulum. Okay, the mass on the end of a pendulum is called the bob. I don't know why. Okay, so we sometimes call it a plumb bob, pendulum bob. Okay, plumb bob, square pence. It lives in a pineapple under the sea, absorbing Taurus and Gemini. You're welcome. Now you're going to have that stupid song in your head all day, because if not for nonsense, it's something to wish. I don't know. I've done that. Yeah, exactly. Don't watch SpongeBob SquarePants. Apparently, you get dumber as a result of watching it. Yeah, I've heard this. Yeah. Okay, so you've got the length of the pendulum. That's an important part of the motion. You do have to have a bob. I mean, there has to be a mass on the pendulum, otherwise it's not going to swing back and forth. While that mass doesn't affect the period, it's also necessary for it to work. Okay, so there's got to be a pendulum bob on the end of that pendulum. Okay? All right, and we'll actually do a lab probably early next week on the things that affect the period of a pendulum. So we'll build pendulums and get them swinging and all that kind of stuff. Okay, so if I wanted to calculate the period of a pendulum, okay, on the top of a high mountain where gravity was 9.71, this mountain would be really high, okay, like beyond Everest, far, far beyond Everest, okay, but let's just say that's where we were, okay, we would just plug those numbers in, t equals 2 pi times the length divided by gravity, and we would get that the period of that pendulum would be 2.51 seconds. Okay, everybody all right with how that works? All right, I want you guys to try this one. I want you to find the length of this pendulum. It'll swing back and forth with a period of 1 second in normal Earth gravity. Okay, give you a minute or two on that. Okay, so for this one here then, okay, if we're looking for length, we got 2 pi times the square root of L over G, so we're looking for something that's under the root, so we're going to have to square everything. So T squared equals 4 pi squared, okay, times L over G. Then we'll just move everything over. So multiply both sides by G, divide both sides by 4 pi squared, okay, that'll get us L. So L will equal 1 squared times 9.81 divided by 4 pi squared, okay, which should give us a period of a length of 0.248 meters. Okay, so it's roughly 25 centimeters long. Okay. Everybody agree with that? Not a hard formula to use, right? Okay. We have, what's here, about 20 minutes, 15, 20 minutes left. I'll let you have a little time to look over your stuff for tomorrow's test. Okay?